Welcome, everyone. Thank you for attending our CMAA New England Chapter June program. My name is Austin Chafee with Jacobs. Before I go ahead and introduce today's speakers, I would like to thank all our New England Chapter annual sponsors. If not for their continued support, we would not be able to bring these types of outstanding programs to our membership and participating attendees, nor support CMAA's mission to promote the profession of construction management and the use of qualified construction managers on projects and programs. Just a few housekeeping details to cover before we begin today's program. Attendees' microphones will have been muted, cameras disabled, and questions may be submitted through the chat feature in the GoToWebinar control panel. If there is time remaining at the end of the presentation, we will attend to your questions. This program is being recorded and will be made available to you via our YouTube channel. Handouts of the slides are accessible through the Handouts section of the GoToWebinar control panel. Be sure to download them before the end of the program. For those of you joining us today for continuing education credit, we will send a follow-up email to you with certification of 1 PDH credit for today's 1-hour presentation. As part of the requirements for PDH credit, I will review the 4 learning objectives of today's presentation. Understanding the strengths and limitations of different non-destructive evaluation methods in condition assessment of reinforced concrete structures. Understanding how to choose the right NDE method for detection and characterization of different defects, using NDE methods to assist in resolving some of non-compliance reports in new construction, and using NDE in condition assessment and existing structures. Today I have the pleasure of introducing Arzu Amani and Michael Brown, both from WSP. Arzu Amani is a senior engineer with WSP USA. She specializes in applying NDE methods to the assessment of reinforced concrete structures. Her NDE expertise includes ground penetrating radar, stress wave-based methods, and corrosion testing. She has been a project engineer and project manager for a broad range of projects, including structural condition assessment, testing and instrumentation, and forensic investigative projects. She has investigated distresses in bridges, parking garages, slabs on grade, historic buildings, post-tensioned concrete structures, and industrial tanks. Michael Brown is a senior engineering manager and senior technical principal at WSP USA. He serves as the firm's USA Bridge Asset Management Lead, where he conducts condition evaluation and asset management of bridges and transportation structures, employs his broad knowledge of materials testing and non-destructive evaluation techniques, develops preventative maintenance, repair, and rehabilitation strategies, and coordinates structural load testing and in situ monitoring, including instrumentation and data analysis. Together, they will be presenting on non-destructive evaluation of reinforced concrete structures. Today's presentation focuses on the use of non-destructive evaluation for both troubleshooting new construction and condition assessment of existing structures. Mike, Arzu, thank you for joining us today. The floor is yours.
Thank you, Austin. It's a pleasure for Arzu and I to join you. I'm going to switch my camera off and go ahead and focus on the presentation. So we want to talk to you today about methods of non-destructive evaluation targeted specifically at reinforced concrete structures. Obviously, reinforced concrete is one of the most ubiquitous building materials in the world, and there are very many uses for non-destructive evaluation to assess either new or existing construction. So what is non-destructive evaluation? We use basic non-destructive evaluation every day. Simple visual inspection or simpler techniques such as hammer sounding or chain drag that are tried and true are truly NDE and provide us very useful information. However, there are a lot of other techniques that we can employ that can give more in-depth information if selected properly to solve or answer questions. So what are some of the goals? Well, to understand unseen conditions can be very useful or sometimes vital for maintaining an existing structure, or to be able to more efficiently evaluate the condition and to do so cost effectively are goals for non-destructive evaluation. The types of applications we're going to talk about today include during construction, investigating issues or non-compliance reports and trying to discern what the extent of a defect or damaged area may be. And then after some mitigation strategy has been employed, following up and confirming that those repairs were done in an appropriate manner. NDE can support all of these activities. So why NDE? Well, it does provide information often about internal features or defects that can't be seen by other means. It can provide objective, data-driven condition data that may be a little bit more repeatable than some of the traditional visual or sounding techniques that I mentioned. It can be used to augment existing inspection regimes to get more in-depth information. And then usually you can collect the data more quickly. It can reduce risk in terms of exposure in some environments, such as allowing rapid non-destructive evaluation on highways and bridge decks to minimize exposure of the workers and risk to travelers. And as I said, it can also be quite cost effective if applied properly. So I'm going to talk at first about some of the basic techniques that are used and their principles of operation. And then following that, Arzu will give some very specific real-world examples where these techniques have been applied. So for reinforced concrete, there is an array of different methods that can be applied. These generally fall into a small number of categories based on their principles of operation, from physical or stress wave methods to electromagnetic wave methods to electrochemical methods. And we're going to touch on very common applications for each of these and give some information about where they're useful and where they may have limitations. We'll start with stress wave methods. So one of the simplest in concept is a technique called impact echo. And as is implied, you use a physical impactor. It could be a handheld hammer, or it could be an automated solenoid. And it imparts a compression wave at the surface of the concrete into, say, a plate or a beam element or something of the nature. And that stress wave is referred to as a P wave, a compression wave, and will travel into the element and then reflect from boundaries back to a transducer or receiver that's placed near the point of impact on the surface. That transducer will translate the mechanical motion into an electrical signal that's collected by a data acquisition system and recorded in what we call the time domain. So you see in the bottom left a typical impact echo signal that starts out with very high amplitude and then dampens rather quickly. Within that signal, there are vibrations at various frequencies that overlap. Through a method called fast Fourier transform, we convert that time domain signal into a representation in the frequency domain. And we interpret the information about frequency to get information about features of the element that we're testing. So in the bottom right, you can see the time domain signal has now been converted to frequency, and there's a very clear peak of frequency that is resonant. In this case, we will refer to this as the thickness frequency for something like a plate element. The thickness frequency is a function of the compression wave and, of course, the thickness of the element that you're testing. Depending on the type of element, there's a shape factor that can be applied, but the fundamental equation for interpreting the thickness frequency is that shape factor times the compression wave velocity divided by the thickness of the element doubled, essentially because you have the time of travel to a reflected boundary and back. And so you would get from the output the thickness frequency as shown in the bottom right corner. That can be interpreted based on the compression wave to determine the thickness of the element. How is this useful for finding embedded objects? So the fundamental test that I just showed gives the overall thickness of an element. However, if an embedded feature or defect reflects the signal before it gets to the far side of the element, you will see a shortened time of travel, and the impact will be a change in the apparent frequency relative to the fundamental thickness frequency of that element. And so you can see here the distance d is shorter than the distance h, and the apparent frequency is then higher than the thickness frequency. If the defect is rather small, you may get a mixed mode response in which part of the signal is reflected from the embedded defect at depth d, and the other part reflects off of the far wall of the element. And so you get multiple peaks in the response in the frequency domain below. So still you see a higher frequency for the shallow defect, but you also see another frequency response that is lower frequency than the fundamental thickness. And the lowering of that frequency is because the wave path travels farther to go around the relatively small defect than it would as if it were a straight path. Another phenomena for very shallow defects is that the defect as a whole can vibrate in a way that's referred to as a drumhead effect. That actually results, rather than a very high frequency response, it actually results in a low frequency that is associated with the vibration of the delaminated element above the very shallow defect. So it's important to understand where these different responses may influence the feedback that you're seeing. Just a quick note about testing conditions. These methods can be very robust, but it is helpful to have a relatively smooth surface to test from. If you were to walk up to a job site like this and try to apply this method, it would be very difficult to get the transducer to mate properly with the test surface and get meaningful results. So you do need to be realistic about how you apply it, and it may be necessary to do some surface preparation before performing the test. Another related stress wave method is referred to as shear wave tomography. As opposed to a P wave or compression wave that is essentially a wave in and out of the specimen, a shear wave is transverse to the surface, the test surface of the specimen, but propagates through the element in the same way, in that it reflects down to a boundary where it is reflected or refracted. And this particular tomography method employs a series, actually an array of transducers that are oriented such that as one transducer imparts a signal, all of the other transducers are in a listening mode and receive response from the signal. So the schematic on the left is showing, for example, that the white lines are the signal from the first array element reflecting to all the other array elements and getting a response. And then in sequence, the second transducer would also impart a pulse shown in the yellow arrows, and all the other transducers would receive that response. And depending on the timing and signal detected at each transducer, all of these can be analyzed together to create essentially a three-dimensional reconstruction of what's beneath the transducer array. Additionally, series of tests of this array can be done on a grid adjacent, working side by side, and then compiled to create a composite. So this method is useful for things like determining thickness, identifying embedded defects, voids called joints, determining location of embedded items such as reinforcement or tendons, and then essentially 3D reconstruction of all of those features that are detected. Here's an example of an image taken of a reinforced concrete element where you can see the location of reinforcing bars in two directions based on a composite image taken with this device. Ultrasonic pulse velocity uses similar principles, but is often employed in what you might refer to as a pitch and catch mode, where you have a transducer at two surfaces of an element and you induce a signal of known frequency from one element and it's received at the other. It's particularly useful in assessing uniformity of the element, quality of concrete, for example, because of the wave velocity through the concrete, which can be affected by changes in its quality. Another somewhat more rudimentary technique that's been around for a long time is called the rebound hammer, also the Schmidt hammer or Swiss hammer. And its principle is to impart a pulse, which is essentially a spring-loaded weight of known mass and velocity, impacting the surface of concrete. And then the response of the concrete causes that mass to essentially rebound from the impact, and the degree to which it rebounds is indicative of the relative stiffness and hardness of the concrete. It can be used to look for variations in quality and strength of concrete, but it can't be used directly to give compressive strength without some sort of correlation against physical test specimens using conventional methods of the same concrete. So you should be cautioned not to try to use this simply to use the calibration curve that comes with the instrument and assume that that's going to give accurate compressive strength. We'll shift our focus to electromagnetic methods. One of the most popular and useful tools is ground penetrating radar. It comes in a wide array of configurations, from small handheld single antenna devices to either cart-based or mobile-based systems that may have one or multiple antennas, or antenna arrays, where the antenna arrays may actually have antennas of different fundamental frequencies and provide complementary information. One of the things to keep in mind with ground penetrating radar is that the depth of penetration of the signal and reflection is a function of the frequency of the signal. And so lower frequencies tend to have deeper penetration, higher frequencies less so. But the alternative is that the wavelength associated with those frequencies means that the low frequency signals do not give as much precision in the response, or accuracy, if you will. So there is a trade-off between depth of penetration and the precision of the features that you can detect. It's often used to find embedded items, particularly reinforcing steel in reinforced concrete elements, and sometimes to also look for areas of potential degradation. Moisture tends to attenuate the signal in concrete, so if you have delaminations with significant moisture, that can be picked up. You can determine thickness of layers. It's not as useful as stress waves for directly detecting depth of delaminations or defects, but it does give some indication. And then can also be used to infer things about corrosion thickness. So again, useful applications: thickness, concrete cover and layout distribution, and also the presence of corrosion-related damage. The way that the system is typically deployed is you have a pair, a transmitter and receiver antenna that are paired together in a particular orientation, and they are scanned over the surface of the concrete. The signal that is put into the concrete goes out in a conical shape. And so even though the information is interpreted as being vertical directly below the antenna, there's actually a conical range in which the signal is imparted. Those signals reflect off of changes in material through changes in what we call dielectric, and sharp changes in dielectric properties of two materials give higher contrast in the response. So for example, here, if the antenna is scanning across the surface from left to right and encountering the reinforcing bars that are embedded, the signal that you see in what we call a B scan, which is a vertical cross section in the direction of the scan, result in the bars showing up as these parabolic features, where the contrast from white to black in this rendering are indicating the change in dielectric at that location. And the amplitude, the higher the amplitude of the reflection, the darker the contrast. Note the second bar from the left has a very light signal. That would be typical of a bar that has perhaps corrosion product or voids around the bar. And what that's indicative of is the fact that corrosion product or voids can tend to dissipate the electromagnetic signal and end up with a lower amplitude reflective response. The reason that we see a parabola, as I mentioned, is because we interpret the signal as being purely into and out of the surface perpendicular to the scan surface, but the actual signal goes in a conical effect. So as you are scanning across and are approaching a reinforcing bar, the time of travel implies that the bar is deeper when you're also laterally away from the bar. And then as you approach the bar, it actually appears to be shallower and shallower until you reach the point where you're directly over the bar. And that's the apparent peak of the parabola. The exact location of the bar can be interpreted through a process called migration, where this parabola is converted mathematically to a point. Let's talk a little bit about some of the electrochemical methods. To assess the potential for corrosion in a reinforced concrete structure, we use what's referred to a half cell to do what's called half cell potential. And the half cell is essentially half of an electrochemical cell, conceptually much like a battery, where you have two electrodes, one an anode and one a cathode. And if you connect them electrically through a voltmeter, and then you have a common electrolyte to complete the electrochemical cell or circuit, you can measure a voltage response, which is a potential of the reinforcing steel and the concrete relative to the reference half cell. This is commonly done in the field with what's called a copper sulfate half cell, which has a porous plug for the copper sulfate solution to ionically bond to the wetted concrete surface to create the electrolyte bridge. With this method, you can measure the relative electrical potential and interpret the likelihood that corrosion is taking place. However, in certain situations, it's better to have a corrosion technologist or expert involved because it's not always straightforward interpretation based on the absolute value that comes out of the test. There are a number of things that affect the response, including temperature, the moisture condition of the concrete, and another thing to keep in mind is that the probability that comes from this is not an indication of corrosion rate. It's only an indication of the potential for corrosion to exist. So the test is done by having the half cell on the surface of the concrete above the bar, connected through a voltmeter, which in turn is connected directly to the reinforcing bar to create the electrical circuit. And as you scan from left to right here across the surface of the concrete, when you reach an area where corrosion becomes active, you see a sudden drop or increase in the negative value of the potential using the method. Those are areas that are indicative of higher probability of corrosion. Electrical resistivity is really meant to measure the properties of the concrete itself and its likelihood to be able to support corrosion, in that if the resistivity is extremely high, then that resistivity will resist the transfer of ions and of current that would support an active corrosion reaction. And the test method is, in this particular case, using a 4-point probe. A current is passed between the external points of the probe, and the voltage is monitored between the internal points. And this is done in the alternating current domain, and the resistivity can then be determined. So higher resistivity, of course, means more resistance to the passing of current and therefore less likelihood of supporting corrosion. Here's an example of this method being applied on a bridge deck in the field. Note that the locations where the tests are being done are pre-wetted, again, to create the electrolyte bridge to support the passing of the current, so that you're getting an indication of the concrete quality and not just resistance at the contact interface of the test device. So that's a quick introduction to a range of methods that we use regularly for reinforced concrete. Here's a quick summary for reference of some of the types of features and conditions that can be evaluated using the different methods. So with that, I'd like to turn it over to Arzu to talk about some real-world examples where these have been applied.
Okay. Making sure I have control. Okay. I'm going to start off by cold joints, which are a bit difficult to detect using non-destructive evaluation. This cold joint here was on the side of a 5-foot thick slab, which was the roof of a radiation room in a hospital. So we can see it at least partially from the side. But the slab was quite large. It was about 80 foot by 30 foot. And to remove and replace the whole thing would have been really expensive. So we needed to use something like non-destructive evaluation to tell us exactly how far the cold joint extended. So we could figure out reasonably how much removal was actually needed. But how can we use NDE to determine the boundaries of the area that's defective? This precast girder was built for a light rail bridge, and you could see the pour line after the forms were stripped. So there were some concerns about potentially having some cold joints. Here is the pour line, and as you can see, the precast plant dry stacked the area. The first thing that we did was we took 2 cores over the pour line, but we didn't see any signs of a defect. Still, the engineer asked for more information through an NDE survey. So we used shear wave tomography to construct a 3D rendering of the test section. This is an overall view of the 3D representation. You see the first curtain, the vertical bars, and here is the second level of rebars. Here's the back wall, and you see the longitudinal bars as well. To have a closer look, we can move these 3 orthogonal planes, which you can see them here individually as well. We can move them to anywhere within the test section. For example, here we see the plan view, which is also called C-scan. So this is the plan view at the depth of the top rebars. And we also see the longitudinal bar behind the vertical bars. And then I can move this C-scan farther away from the test surface, and then I can see the second level of rebars. But you can still see the first level of rebars, which would be these red dots here. And this is just showing the cross-section at the depth of the first level of rebars, which is superimposed on a picture of the girder for better visualization. For this particular example, we did not find any discontinuities. And as you can see, there are no reflectors other than the rebars. So no cold joint was detected here. Another common problem in construction is honeycombing, which can be caused by improper placement or poor vibration, or because of using the wrong mix for a given rebar configuration. For example, if the aggregates are too big for the rebar spacing, we won't be able to have proper consolidation, and then we'll end up with voids in concrete. This is an example of honeycombing caused by improper placement. You see that this is a heavily reinforced wall, and because of the reinforcement congestion, it was challenging to place the concrete, so they just dropped it. They just dropped the concrete. As a result of that, the coarse aggregates ended up segregating during the free fall, and the contractor did not have a vibrator which was long enough to reach the bottom of the form, and that's why they ended up with honeycombing here at the bottom. These are some of the technologies that we can use to look at honeycombs. And it's important to note that regardless of what kind of technology we end up using, the NDE findings always need to be validated using some limited ground truth like coring. This is a water reservoir, and these are the rebars for a 3-foot thick slab. As they were pouring concrete, one of the vibrators broke. And afterwards, when they stripped the forms, they saw that some porous areas appeared on the edges of the slab. So there were some questions raised whether concrete was properly consolidated or not. Here are the results of our investigation. Here again, we can move these 3 orthogonal planes to look at any cross-section. This is the plan view or C-scan, which you see here as well. You clearly see the rebars, and no honeycombing was detected here. Another common problem in both new construction and existing structures is delamination or debonding. Stress wave methods are the most effective technologies in finding delamination, but depending on what the cause is, GPR can also be used. For example, if delamination is corrosion induced, we may also be able to use GPR. The results that we get from NDE are not always as straightforward and as easy to interpret as the 3D renderings that we saw earlier. This is a pedestrian tunnel in a golf course. This was an overhead shotcrete application, and it was on a rainy day, and the concrete was too wet by the time they started the second lift. And that's when the inspector noticed some sagging and issued a non-compliance report. So we did some testing. As you can see from the results, there are just way too many reflections here, and it's just not practical to have a definitive interpretation for every single one of them. But we were looking for potential debonding and the crown. We were looking for debonding in the crown, and this strong reflection here seems like a good candidate for that. We took a core exactly here, and as you see, we found some major debonding. So although we may not be able to interpret everything, but we can gain enough information from a non-destructive evaluation survey to help us make a more informed decision as to the next steps. The other common problem is inadequate rebar cover, and GPR is the best NDE method to find rebar configuration and rebar depth. This is a newly constructed bridge. The bracing for the north exterior girder was insufficient to prevent displacement during the pour, and as a result of that, the concrete cover on the north half of the deck was compromised, as you can see in these pictures. So in some areas, the reinforcement is even completely exposed. This is the cover map based on our GPR survey, and you can see that in the north half of the deck, the rebar cover is mostly less than 1.5 inches, which is a light green and warmer colors. And even for a good portion of the deck, the cover is even less than 1 inch, which is orange and warmer colors. The contractor ended up removing and replacing this part of the deck because GPR gave us a quantitative measure of what percentage of the deck had inadequate rebar cover. And this is the same cover map superimposed on a picture of the deck for better visualization. For thickness verification, we can use any stress wave methods. This is the same bridge that we just saw. Looking at the bottom of the deck, you see that we have stay-in-place forms right here. We did an impact echo survey on a very fine grid just for thickness verification, and save for one spot, which would be this. Impact echo was quite accurate in detecting the top and bottom of corrugation. This is the 3D rendering, and this is the plan view. Orange is the top of corrugation, and yellow is the bottom of corrugation. So except for one error, impact echo was quite accurate. We can use different NDE methods to see if post-tension ducts are fully grouted or not. For example, impact echo is quite effective. This example here shows a laboratory specimen which has a steel duct, and only half of it is fully grouted. So this half is grouted. And the slab also has an artificial delamination here on the left. They tested the slab using impact echo on a fine grid, and let's look at the results. As you can see, we get a completely different response where the duct is fully grouted as opposed to where it's empty. You also see that impact echo obviously captured delamination quite well as expected. Now, as I said, this test was done on a fine grid, so it was possible to generate this map, but in the field, we don't have the luxury of time to do our testing on a fine grid. So it becomes really important to be able to interpret the individual frequency spectrums to see if we have any voids in the ducts. And in order to do that, we need to review some theory first. This is the simplest case for impact echo application, which Mike talked about earlier. For a solid section of a concrete plate, which has no defect and no reinforcement, the spectrum is going to have a single dominant frequency, which we call thickness frequency, and it can be calculated using this equation. Now, if we have a fully grouted duct, the spectrum will have two distinct peaks. The first one, this f of h, is exactly the same as the thickness frequency for a solid plate, as you can see here. And the frequency for the steel duct is going to be calculated using this equation. Now going to the other extreme, when the duct is ungrouted, the thickness frequency shifts to smaller values compared to a solid section. This red dotted line from up all the way down, this shows where the thickness frequency should have been if we had a solid plate or if we had a fully grouted duct. This lower frequency is called shifted frequency and is an important indicative of potentially having voids in a PT duct. The other thing that we notice is that for ungrouted duct, we are going to miss the peak for steel, which should have been where the blue line is. But then we'll get a higher frequency for the void, which is calculated using this equation. It's important to note that looking at these two pictures, the void and the duct are obviously located in the are placed in the same location compared to the test surface, but they have completely different characteristics, which is why it's important to do these calculations before going to the field to know exactly what to expect and how to interpret the results. It also shows why it's important to do impact echo analysis in frequency domain as opposed to time domain. Now, for partially grouted ducts, the response is going to be a little more complicated, and it depends on the location of the void with respect to the tendons and also with respect to the impact direction. For example, in the first case here on the left, the results that we get may look like as if this is an ungrouted duct, even if we have a really small void. Whereas for the second configuration, a small void may not even be detected at all. So the results may appear as if this is a fully grouted duct. So looking at these two scenarios, we see that we may have the exact same size void, but we'll get completely different results because of where the void is located with respect to the impact surface. It also shows why we always want to use multiple complementary technologies in the field to piece the puzzle together, because we just can't get all the answers from a single technology. And for the last scenario, which is the most complicated case, we may get responses from both the steel and the void. Even if this is the case and we have multiple peaks, we can still say that there might be some voids because of the shifted frequency. So the shifted frequency is the most important indicator that the duct is probably not fully grouted. Now, with this information, we can look at an example to see how it actually works on a project level. This project involved examining PT ducts in a pier box. The first thing that was done was that the duct was located using GPR, and then starting from the top going down, impact echo was done at every 6 inches. Here in the middle, you see the frequency spectrums, which are from about 5 foot to 15 foot measured from the top. Now, if we look up here, we see that the peak frequencies are all over the place. And you can see the shifted frequency, which would be these black lines. The black lines show the shifted frequency. In contrast, it gets pretty steady down here. The red lines show the thickness frequency, which is consistent pretty much for these highlighted spectrums. So based on this survey, it was concluded that the duct was probably partially grouted in this upper part, where you have the shifted frequency. And then they drilled some holes and used a borescope to look inside, which confirmed this conclusion. So this is how we use those boring calculations that we talked about a few slides earlier for an actual project. It's just important to have this background information to be able to make sense of the data in real time when we are in the field, so we can make adjustments if it's necessary. NDE can also be used for as-built verification. Here on the left is an AASHTO girder, and you can even count the number of tendons, and you can move display and you can move it up and down to see a different cross section if you want. And here on the right is a bridge header, and you see the serves. We can have a closer look at the bridge header, but at a different cross section. These are the girders as we identified using NDE. The red ones are the girders. And when you compare this with the plans, you see that the girders locations were captured quite accurately. We can use non-destructive evaluation to determine the tendon configurations in pre-stressed girders. There are many older pre-stressed bridges that don't have structural plans. So when it comes to load rating, it will be very helpful if we can accurately reconstruct the 3D representation of these girders. Here's what we get using GPR, which really isn't much. At best, we can get some information about the number of tendons close to the bottom of the flange. Now let's see what we can get using shear wave tomography. Oh, this is actually how we collect the data from the bottom of the girder. And this is an overall view of the tomography results. You also see the outline of the girder for better visualization. When you look at the B scan, which is the girder's cross section, we can identify at least 3 distinct layers of tendons. But for more details, we need to look at specific cross sections. As I move to a different depth, please pay attention to C scan and volume. So these two views down here. First cross section, we can count 10 distinct reflectors at the bottom of the flange. The 2 on either side are probably conventional mild steel, and that would leave us with 8 tendons at the bottom of the flange. Moving a little bit farther away from the test surface, we see 6 tendons in the second layer. So again, I'm moving this C scan, which is the plan view. I'm moving this away from the third level, from the test surface. Now moving a little bit farther away, in the third level, we see we can identify 2 tendons. So compared to GPR, shear wave tomography gave us much better picture, at least for this particular project. A little bit simpler example is this hollow core slab. We can reconstruct the extruded voids and the tendons. Here's the migrated GPR profile, which confirms the results from tomography. The examples that we looked at so far focus primarily on the use of shear wave tomography and impact echo. Although shear wave tomography in particular is a great technology and gives us a lot of information, it's just not the most rapid technique, because if you want to create a 3D rendering, you have to test on a 6" by 4" or even a smaller grid. So it takes a bit longer time. This example shows the use of GPR for verifying the rebar configuration in an underground parking garage. There were some concerns that the construction of some of the columns was not done per plan because there was some cracking and some deflection. So the structural engineer wanted to see the reinforcement configuration around the column, and they were considering adding some drop panels afterwards. Here are the results. This one shows the results of our survey from the top. These are actually from 8 different individual surveys that are stitched together. And this one shows the results when we surveyed the slab from the bottom. Mike mentioned earlier something about GPR frequency and the penetration depth. The reason that we had to survey both from the top and the bottom was that the slab was 18 inches thick, but the depth of penetration for the GPR system that we used was only 12 inches. So we had to test both from the top and the bottom to entirely cover the full thickness of the deck or the slab. So again, it's the objective of the investigation which determines which technology we should use. We could have also used shear wave tomography here, but it would have been unnecessarily more time consuming and more expensive for the client. We can use multiple technologies together for a comprehensive corrosion investigation. If corrosion is chloride induced, using GPR, half cell potential, and electrical resistivity combined together, they can give us a pretty good picture of the existing condition. This first map up here is the GPR attenuation map for a bridge deck. And the second map here is the corresponding half cell potential map. We see that the areas that GPR identifies to have higher attenuation also appear to have higher probability of active corrosion as identified by half cell potential. And as always, NDE results need to be validated using some ground truth information. We've talked about the strength of different technologies, so it's good to look at some limitations too. This is a spillway for an old dam, which has limited structural drawings, and we were asked to determine the thickness of the slab. First of all, we drilled a pilot hole, and even after 30 inches, we still didn't reach the bottom of the slab. So the next thing was we did a GPR survey using a lower frequency antenna to get a higher penetration depth. Looking at the GPR profile, we got a very strong reflection at a surprisingly shallow depth. The reflections were coming from less than a foot deep, even though we were expecting them to be at least 3 feet down. Then we took some cores and saw that there was a wide water field delamination anywhere from 6 to 8 inches deep. So what does this all mean for our investigation, and why couldn't we make sense of our GPR data? For GPR application, there is this thing called the reflection coefficient or reflectivity, which basically tells us how much of the GPR energy can actually penetrate into the substrate. For wide water field delamination, the reflectivity is 0.5, which means 50% of the incident wave is just lost off the bat before even reaching concrete surface. The other thing is that a ground couple antenna should be either in direct contact with the ground or within a maximum 10% of the wavelength, because that's when the greatest amount of energy is capable of transmitting through the substrate. So we have two issues here working against us. One is the reflectivity, and one is the fact that the delamination was just too wide, even greater than 10% of the wavelength, so ground coupling was lost. What this means is that the GPR signal for this particular profile that we just saw was collected. So the signal just could not penetrate to the bottom of the slab, even though the antenna that we used should have theoretically seen up to 40 feet deep. This shows the importance of designing the survey ahead of time, and also shows us how important it is to have the flexibility and the ability to modify the survey when you are in the field. For example, if you had planned to collect your profiles every 4 feet, after seeing this, you may decide that it makes more sense to have a denser grid. So maybe you collect the data every 1 foot. So basically, it's important to be mindful of NDE limitations. We don't always get what we are looking for, and we need to be flexible to adjust our survey plan in real time. The other thing that this example highlights is the importance of gathering ground truth information. We couldn't have known what was going on without this course. To wrap things up, NDE is just a tool in our condition evaluation toolbox and for a comprehensive condition assessment. In addition to non-destructive evaluation, we need some physical sampling for ground truth and validation. We need laboratory testing, for example, to determine chloride profile or compressive strength. And sometimes we may need petrographic examination as well. Then we can use all this information plus the information that we get from the plans and visual inspection to come up with the appropriate repair procedures. Just to summarize, we can use NDE for investigating both new construction and existing structures. Each NDE technology has certain strengths and limitations. It's the nature of the problem and the objective of the investigation that dictates what technology we should use. Benefits of NDE. With NDE methods, we can reduce destructive probing. We can investigate a larger area in the same time frame, and we can also have a more comprehensive assessment of the structure. And finally, we always need some limited destructive probing to ground truth or to validate the NDE findings. With that, I thank you for your time. If you have any questions, we'll be happy to take them now. And our email's on your screen. Feel free to reach out to us afterwards if there are any additional questions.
All right, wonderful. Thank you, Arzu and Michael. And I guess I'll invite you both to turn your cameras back on. To our audience, if you have any questions, please put them into the chat feature now. While I give you a second to do that, I think we might have time to answer one or two. So let me start us off. So why should a client spend money on NDE when sound testing can tell them where delaminated areas are?
Okay, Arzu, you want to take that one or me?
Go ahead, go for it.
Sure. Well, sounding is obviously a long-standing method and can be very useful. And so we don't discount that it is popular and gives good basic information about existing damage. However, there are limitations. Sounding is subjective. It depends on the experience of the operator, and that it's affected by, for example, ambient noise and even the, I hate to say it, but the age of the operator and the quality of their hearing. I know that firsthand, but some of these non-destructive techniques actually can get better information. They can detect deeper defects that can't be heard in the audible spectrum by a typical human ear. They also have the benefit of they're typically tied to some sort of a spatial measuring system so that you get location information that can be reproduced much more easily. The data is collected spatially in a more automated fashion, and it's easier to create permanent records. So there are a number of benefits. Some of the more modern deployments of this technology can do these things even, you know, like a whole lane of a highway at a time at a pretty reasonable pace, much more quickly than can be done by hand and documented. So there are a number of reasons why you might do that.
All right, wonderful. So I haven't seen any questions come in, and I know Mike and Arzu's contact information flashed up on the screen only briefly. So I would encourage attendees to submit questions to CMAA directly, and we can pass your questions on if you didn't capture their emails. That would be at info@cmaa-ne.org. I'd like to thank our speakers today. This was a very educational and insightful program, and I'm hoping that our attendees got a great deal out of it. I'd like to thank our attendees for joining us today, and I'd like to thank our sponsors once again for supporting the chapter and allowing us to put on these programs. Without further ado, I'll wrap it up and thank you all.
Thank you.
Thank you, Austin. It was a pleasure.